Here we're going to look at doing some dot structures for some kind of out of the ordinary species. So we still want to try to satisfy the octet rule if possible, but we might have to do some kind of creative manipulation of the electrons to do that. So here we've got nitrogen and oxygen. And so we're going to put the nitrogen in the center. We'll put the oxygens on either side. We have 18 electrons to work with. The 17 from the atoms, and then the negative charge gives us one more. And put the bracket up there. We'll kind of go about our general pattern of doing a dot structure. We have one more pair left over, so we can put them in the central atom. And now we look at the nitrogen, and the nitrogen doesn't have a stable octet. So we need to consider double bonds. And in this case, we have an option of taking it from the oxygen on the left, right? Or we can take it from the oxygen, the other oxygen. So if we do that, we get this structure here. And these two structures are referred to as resonance structures, and they're separated by a double arrow. And so these would be two equivalent resonance structures. Each one is no more valid than the other. So what it's showing is that the electron density between the nitrogen and each oxygen is somewhere in between, 2 electrons worth of density and 4 electrons worth of density. Neither one of these pictures is totally correct. When we study more of the bonding theories, we'll get a better picture of how this functions. But with dot structures, this is about as good as we get. All right, here's another one that is slightly unique. We're going to put the elements in the order that they're listed. No ions, so we're going to put the bracket up there. This time we have 16 electrons to work with. Again, we'll do our kind of standard pair the bond, and then complete the octets of the atoms connected to the central atom. This one ends up looking a lot like carbon dioxide, and so our tendency is to form double bonds on each side of the carbon and call that good. However, in this case, we have two different elements on each side of the carbon. We've got sulfur on the left and nitrogen on the right. I could alternatively make a triple bond on the nitrogen side and a single bond on the carbon side, and this would also satisfy my octet rule. These are both resonance structures of each other, and of course I would get a third structure by putting the triple bond on the sulfur side and leaving the nitrogen side with a single bond. So how do we evaluate these three different structures? Well, we evaluate these by looking at what's called the formal charge. And the formal charge is the difference between the number of electrons that an atom has, the valence electrons that an atom has that come into the bond, compared to the number of electrons that the atom has with the bonding, the way that it's drawn. So, for instance, if I look at the top structure and I look at the sulfur, sulfur came in with 6 valence electrons. Sulfur now has four electrons that it has all by itself, two lone pairs, and then it has 4 that's sharing with carbon, so it gets half of those. So sulfur came in with 6, and it ends up having 6. So it's got a 0 formal charge of that top species. If I look at the next one, carbon's gained some electrons here. So it's got 6 all by itself, those 3 lone pairs. And then it gets half of what's involved in the bonding, which is 2 more electrons, so it's half of that. So in the second one, sulfur has a 1 minus formal charge. And then we look at the bottom picture, and sulfur kind of loses out here. It's going to have 2 by itself, and then half of those 6 that are shared, which will give it 5 electrons, or a 1 plus formal charge. So you see that sulfur gets different charges in each one of them. If I look at the carbon, carbon has 8 bonded electrons in each one of the pictures. So it gets half of that, so it gets 4, and it came in with 4, so the carbon has a 0 formal charge in each one of them. So that's not going to kind of factor. Next, we look at the nitrogen. So look at the top one. Nitrogen came in with 5. In the top picture, nitrogen is going to have a 1 minus formal charge. It's got 4 by itself, and then it's sharing the other 4, so it gives it 6. And it came in with 5, so it's got a 1 minus formal charge. Now, we can also notice, now we put all the formal charges in, that when you add those formal charges up, they have to add up to the overall charge on the ion. So we can kind of imagine what the formal charge on the next one's going to be without even adding it up. It should come out to be 0, but you can confirm that it's got 2 by itself, and then it's sharing 6, so it's going to add up to 5, which is the nitrogen came in with. And then the one on the bottom, nitrogen has 6 all by itself, and it's sharing 2, so it's going to have a 2 minus formal charge. Now, when we think about covalent bonding, we think about electron sharing, or atoms sharing electrons, because they all want to gain electrons. Like, have strong attraction to the electrons. So the idea of formal charges, if you have large formal charges, that's not very favorable in covalent bonds. So we can right away kind of assume that this bottom one is not going to be a very major contributor in how we think about this binding. And that's really what we're trying to do here. We're trying to understand how is the electron density distributed in the species. Now, the top two are pretty similar. The one has nitrogen with a minus 1 formal charge, and the other one has sulfur with a minus 1 formal charge. Well, if we look at the electronegativity, nitrogen has a higher electronegativity, and so it makes more high electronegativity than sulfur. So it makes sense that the nitrogen one, where nitrogen has a minus formal charge, is probably the preferred resonance structure to the one where sulfur has a minus 1 charge. So we might say that this would be the major contributor. That would give us the best picture of what this looks like, and this other one might be a minor. And so using formal charges, we can make that kind of evaluation. And again, we kind of recognize that we need to do that in this one because we have those different types of elements, the atoms of different elements that are involved in this bonding. So the choice of where we create the double bond would create different formal charges. So we want to just be aware of that. Here are some structures of benzene. Benzene ends up being a really important molecule in organic chemistry, and it's because of the resonance structures that form with benzene. So we'll get talk more about this in class. This is kind of an important bit for us to learn and apply chemistry to organic molecules. SF4 is going to present us with our first expanded ion. So if go ahead and put all of our elements here, and we count out the number of electrons that we have 34 valence electrons in sulfur and chlorine. That's and we still have 6 left over. Much left here. And what it does then is it gives us a sulfur that has or if we do this with any of the elements that are or lower that have a little bit more size in it, most comfortable a little bit but and have
is better than the other. We'll talk about that.